formula হ্যাঁ তোমাদের কেমিস্ট্রি কিন্তু অনেক ডেফিনেশন আসে ইনফ্যাক্ট A2 তে you can just study definition and get a B আর কিছু না শিখে just definitions না way more but the exam is 100 marker একটা paper so এই 100 mark paper এর মধ্যে প্রত্যেকটা কোশ্চেন হচ্ছে 2 বা 3 marker definition থাকে there are 15 questions out there so you can get like 45 marks just by doing definitions and A তো হচ্ছে 51 এ so অনেক সময় এও পেয়ে যেতে পারো right so that's the definition of spring constant yeah word formulas not simple yeah কিসের জন্য বলো what do you write word allow করার কথা তো what's the definition they accepted বলে নাই আচ্ছা না definitions word physics definitions word লিখতে পারবা formula দিয়েও লিখতে পারবা কোয়েশ্চেন থাকলে আমাকে বলো এই প্লাস মাইনাস যেটা এটা বললাম তো এটা অ্যাকচুয়ালি trivial মানে এটা just you might find it somewhere suddenly and that might you know make you curious the minus কেন দেওয়া doesn't really do anything it's symbolic মানে কি it's just there to show that they're in opposite direction it doesn't change your math at all is there any way to make a spring elastic when it's already reached the elastic limit such as applying heat not that I'm aware of. Temperature doesn't usually impact elasticity of materials.
What about those things, those materials that retain their original shape of
No, there are materials like that. Thermo, yeah, I forgot the word. It's basically if you heat them, they go back to their normal shape. ওটা প্লাস্টিক ওটার ইলাস্টিক বিহেভিয়ার নেই কোনো জায়গায় ওটা হিটে হচ্ছে এটাকে রিফর্ম করা হচ্ছে সো ইটস এ কেমিক্যাল রিঅ্যাকশন আর ইউ গাইস ডান ওকে আগে এই জিনিসটা বেসিক ছিল ওকে লেটস গো টু পেজ নাম্বার 16 এর পাশের ব্ল্যাঙ্ক পেজটা আছে এটা নতুন আর এটা ইম্পর্টেন্ট ওকে এটা নিয়ে অনেক এমসিকিউ আছে দিস ইজ elastic strain energy or potential energy. Okay, look at this very carefully. Complicated, right? So look at this spring here, and we have not gone beyond the elasticity. Look at some spring থেকে force নিয়ে গেলাম, and যখন force arrow outward হয়, the process is called loading. Loading হচ্ছে when you apply a force to deform your spring. And as you load a spring, মানে যে mass দিলাম, এই process থেকে loading বলা হয়, okay? As you load a spring, what happens is it stores energy in it, right? এখন energy কেন store হয়? Let's try to understand. You take a spring here, and you want to deform it. So you want to get the force apply করবা, F. As you apply the force here, the spring will extend, right? So এখানে একটা ছোট extension আসবে. And from the ideas of work, power, and energy chapter, whenever you apply a force, then there's distance moved in the direction of the force, right? What is being done? Work, right? So you're actually doing work on this. I'm যখন এটাকে stretch করার চেষ্টা করতেছি, I'm doing work on the spring. And the work that I do is transferred mechanically and stored here. And work করা কিন্তু it's a process. Work is not a form of energy. Work is a process of providing energy. So when you work, apply a force on a box, right? What does the box start to do? Move. What does it gain? K. If you do work on an object and raise it up, what does it do? Gain GP, right? Similarly, you take a spring and do work on the spring. What does it do? Is it stores energy in it, right? And the graph here will store energy. So আমাদের বের করতে হবে গ্রাফ থেকে energy storeটা কোথায়. So I showed this before O level say একটা idea that if you want to find what quantity of the graph gives you what, right? You compare their units on the axis, right? So যদি এই গ্রাফের gradient কেউ জিজ্ঞেস করে what is the gradient? What would you do? F by x, and what does the gradient give you? Spring constant, right? What is the area under the graph? Right? কি হবে? Like what do I do? What do I multiply? The y-axis into the x-axis, do you remember? So area would be change in y into change in x. And in this case, it's a triangle, so it's going to be half fx, right? And what do you get when you multiply force into distance? Work done, right? Bottom line to boli. Bottom line to hoche, the area under this graph gives you the energy stored in the spring, okay? And this energy that's stored in the spring is referred as the elastic potential energy. So তোমার গ্রাফের যে নিচের যে এরিয়াটা এখানে, it's called elastic potential energy. It's the energy stored when you stretch your material. But there's a very big problem, okay? I'll tell you what the problem is. So সবাই একটু carefully দেখো. What did I apply onto my material to stretch it? F force, right? So that's the value of force, F. And it underwent an extension of x, okay? So it's an extension of x আসছে. So if I want to find the work done, what's the formula for work done? Normally, force into distance, right? So shouldn't the work done be just force into distance? That should be the work done on the spring. But the energy stored in the spring is not force into distance. What is it? Half force into distance, right? So what's actually happening here is that the work that you did was this area. This whole thing here is the amount of work that you did. Don't force into distance, right? But the actual energy that is stored is what? Half. Why? And why? And why is it lost? তোমার কি প্রবলেমটা বুঝছো? I'll obviously give you the solution. প্রবলেমটা হচ্ছে that whenever you do work to stretch a spring, always the energy that's stored is what the value of you provided. Half. Exactly half. Can exactly half? That's not part of our syllabus though. No, we K eventually convert to it as storage. No, there's no bond breaking here. No. It's a permanent deformation. It's within the elastic limit. আচ্ছা আমি বলি কি হচ্ছে what happens here is as you take the spring, right, as you try to stretch it, do you think that the spring is just moving, or do you think that the spring is also applying a force against my movement? মানে আমি যেটা বলতে চাচ্ছি, আমি যে স্প্রিংটাকে নিয়ে এভাবে মুভ করি, যেই ফ্রিডমটা এক্সপিরিয়েন্স করব, আমি এটাকে নিয়ে যদি এভাবে মুভ করি, will I feel the same freedom? No. কি ফিল করতেছি? এখানে একটা tension, resistance, right? So what is found is that whenever you do work on a spring, the amount of force you apply and the distance that you travel, right, there's an equal opposing force right? That's working against you.
Tension.
Yeah, so this tension. So the idea is that as you try to take a spring and stretch it, right, the spring opposes you, and you need to do work against the resistive force from the spring. And that's the place where the energy is lost. So every time you try to stretch a spring, তোমাকে কিন্তু free ride না. So you remember I told you just নিয়ে যাওয়ার মতন ওইটা না কিন্তু force into distance. তোমাকে something এর against a work done করতে হচ্ছে. And whenever you do work against something, I talked about this, a very important point. Do you gain energy or lose energy? Yeah, so that's why energy is lost, and that's why the whole thing is not out there. But I'm যদি হচ্ছে, if I just take this and apply force and move it, there's no opposition, no resistance. যা force দিচ্ছি, যা distance দিচ্ছি, that's my work done. But এখানে যেটা হচ্ছে, as I try to do this I have to do work against an opposition, right? And that is taking energy away from me. Now, why is it half? এটা তোমাদের syllabus নাই because you don't have integration. So it's based on integration. So এই গ্রাফের একটা integral থাকে work done ওইখান থেকে এটা আসে, okay? But I still want you to know something about this. So do you guys know how to integrate?
Yes.
We do not have integration in math, in physics here, okay? ওই পার্টটা নাই, we don't have calculus basically. So what is the original definition of work done? এটা একটু বুঝাইতে আমাদের, যাতে তোমার একটু পিকচার করতে বেটার হবে. The official original definition of work done is an integral of the displacement function with respect to force. মানে তুমি কি করবা, তুমি হচ্ছে এই গ্রাফটাকে ইন্টিগ্রেট যদি করো, aren't you not integrating this with respect to the x-axis displacement and what's the y-axis? Force, right? A y-axis যখন force হয় and you integrate with the x-axis as your displacement, the area always gives you the work done. And that's the main reason why we plot what graphs? Force versus extension. So surprisingly, এখানে problem হচ্ছে না. এখানে কিন্তু আমি যদি এই এরিয়াটাও বের করি, what will I still get? The same amount of work. But যখনই গ্রাফটা একটু এদিকে bend হয়ে যাবে, let's say, right? Do you think this area under this graph and that area under that graph are equal? Absolutely not, right? So one has to be right. Which one is right? The one that's under the force extension graph, not the other one. Eta jodi koro, which I feel like you did in math, তোমরা যদি with respect to the y-axis করো, integration করা যায় কিন্তু তখন কিন্তু it's not the definition of work done. Work done is not a function of f, it's a function of x. মানে the equation is based on x, okay? So x কে আমরা integrate করি. So that's the reason why mainly a graph গুলো সব force versus extension হয়. That's the real reason, okay? Extension versus force দিলে তোমাকে y-axis integrate করতে হবে, which is not normal. আচ্ছা, so anyways, আমাদের এখানে কি জানতে হবে? I'll give notes on these, don't worry. ছোটখাটো জিনিস ওরা অনেক জিজ্ঞেস করে এখান থেকে, so I'll provide notes. But main thing right now is that the area under the graph is the elastic potential energy or elastic strain energy. I mean, interchangeably a word গুলো use করবো so that you also get used to it. Strain ও লিখতে পারো, potential লিখতে পারো, problem নাই. আচ্ছা, একটু এদিকে পরে লেখো, আমি একটা গুছায় সবকিছু দিব, তখন you'll find it easier to copy because you'll understand what you need to do. So yeah, this is just stretching a graph, and এখানে হচ্ছে if I find the area under the graph, তাহলে elastic potential energy formula কি হবে? Half f x, right? But we also know that f is equal to what? Kx, right? তাহলে আরেকটা formula আছে half kx square. And this one you'll find is very handy in terms of MCQs. কারণ অনেক MCQ তে ওরা spring constant দিয়ে দিবে, ওরা হচ্ছে তোমার extension দিয়ে দিবে, বলবে find work done. স্টুডেন্টরা কি করে, ওরা ওয়ান্ডার করে তাহলে half fx আমার force বের করতে হবে, so spring constant extension use করে force বের করে, তারপর half fx করে. What could you have rather done? Half kx square. Okay, it's much easier. Also এখানে আরেকটা ইন্টারেস্টিং জিনিস নোটিস করবা, that for a spring, right, for every amount of extension you increase, the energy increase is actually a square factor. মানে একটা স্প্রিং কে যদি আমি এক্সটেন্ড করি by 1 centimeter, যা এনার্জি স্টোর করবে 2 centimeter এনার্জি স্টোর কিন্তু 4 times. You know why? Half kx square. Extension যদি double হয়, isn't that getting squared? So what is the energy going to become? 4 times, right? So তার জন্য if you stretch a spring 3 times, right, the energy is substantially higher. আমি তোকে দেখাতে পারি এখানে, এটাতে দেখো what's the return? Very slow একটা return, এই যে এখান থেকে ডাবল করলাম, That's quite fast, right? Triple করলে it's gonna fly, right? So do you see how fast it went? It wasn't increasing linearly, what I'm trying to say. It's increasing exponentially. And the reason behind that is this formula. So the energy stored gets higher and higher. And there's another place in physics where this matters. Do you know where? On this Lewis acid. Past paper করতে গেলে you'll find this quite often. Another place where যা বুঝালাম এই সেম জিনিসটাই হয়। না না অন্য চ্যাপ্টারে ইলেকট্রিসিটি না is মূলত করে আসছে আমরা এই চ্যাপ্টারটা করে আসছি so tell me a place where this same relationship exists terminal velocity no yes kinetic energy problem ki if your car is moving at 10 meter per second right 10 meter per second মানে হচ্ছে you're traveling at the speed of let's say a rickshaw and you hit the wall like but you'll get a dent maximum right if you're traveling at 20 meter per second which is just double right and your car hits the same wall if it's the front end has collapsed right so speed beshi barne kintu from 10 to 20 is an impact increase of how many times 4 times and that's the reason why if you're going from 10 to 50 right your car's K increases 25 times so you'll find চোখের সামনে যদি গাড়ি দুটো বাড়ি খায় you'll see this slow but what is the consequence of it it's much more drastic right they store a lot of energy they store square amounts of energy same as this okay so just keep that in mind there's this square factor here why is it x squared f হচ্ছে kx into x is x squared our question হচ্ছে why does it get higher subtraction because it's the more you go the more resistive force so it doubles in effect acha screen it let's move on so next হচ্ছে what if you unload it so loading হচ্ছে when you stretch the graph right and unloading হচ্ছে when you release the force and when you unload your graph right the elastic potential energy is released and returned as what energy এখানে করলাম kinetic energy right so আমি একটা spring কে নিয়ে stretch করে ছেড়ে দিলে doesn't it move right so this is when the EP is released as K but the main thing release as K থেকে যেটা বড় ব্যাপার is that am I getting all my energy back no graph দেখে বললাম okay if the line just goes straight down right am I getting exactly the same energy back yes why would you not what's the problem কেন হিট হবে না কই এয়ার মলিকিউলস এখানে এয়ার মলিকিউলস হচ্ছে এখানে বাড়ির কাছে এয়ার মলিকিউলস তো ভিতরে চলে it's a hollow thing no so there's no energy loss so in a perfect scenario where there is let's say in a vacuum okay always imagine things in vacuum so in a vacuum will there be any energy loss no and look at the graph যেটা হচ্ছে graph isn't the area under the graph for unloading exactly same as loading তাহলে কি হবে কোনো এনার্জি লস হচ্ছে না okay so that keep that in mind because order parted it becomes important so now we will move away from this কেন because এইটা দেয় না ওরকম ওরা যেটা mostly the exam is one of you said what if there's sound Arjun also what if there's recoil after the spring has collapsed ভালো আমার এই যে elastic potential energy is now converted to Ke plus what sound plus বলছে jump করছে so GP so I'm getting back my energy ওটা তারপরে কি হয় it's issue right not my issue so এখানে the GP the EP is given back to me that's what's more important acha let's move on so এখন your material has permanently deformed and এই যে এরকম হয়ে গেল এই পার্টটা হচ্ছে complicated so see what happens so once again what does the area under the graph still provide you work done and the EP stored so তুমি একটা material কে যদি stretch করো and you permanently deform it it still stores energy in it right so the area under the graph here represents the energy that we have provided so this area here right represents the energy that was given to your spring and ওই যে energy provide করলো পুরোটা কি spring কে stretch করতে use করা হচ্ছে or some of them were used to break the bonds মানে যে এখানে যে এনার্জিটা আমি শেড করলাম is it the energy needed to stretch the spring only or is some of it used to break the bonds yeah it's used to break the bonds what deformation has taken place here permanent deformation so এটা হচ্ছে total energy provided. So what you see here is the total energy that you had provided to the system. Okay, are you with me so far? Kono confusion থাকলে বলো, হ্যাঁ বলো। So আচ্ছা, এটা পরে একটা গ্রাফ দিয়ে বলতে চাই। So এটুক দেখাচ্ছে the amount of energy I've provided. এটুক কি okay? That kind of work done হচ্ছে, force দেওয়া হচ্ছে। Right now, the thing is, if I get rid of this force here, এই ফোর্সটাকে আমি যদি ছেড়ে দেই, right? তাহলে কি হবে? So I've taken my spring, practically দেখাই। So you have your spring here, এই পার্টটা, okay? And I stretch it, unstretch it, it comes back, right? So if I stretch it, unstretch it, it comes back. Now what I do is I stretch it, right? And I permanently deform it, okay? এখন permanent deform হয়ে গেছে। Do you think if I release it, it will go back? Yes, that's important, okay? So do you think, will it go back? Yes. Will it go back entirely? No, right? So that's a very important thing. A lot of students don't believe it goes back. They will feel that elastic deformation মানে হচ্ছে size change হয়ে গেলে it will stay there. It doesn't stay there, it goes back. See, it's not much longer than before, but didn't it go back? It went back pretty well actually, right? So what does that mean? It means that, do I lose all the energy I provided or do I still get back some? Yes, right? So how do we figure that out? So এখানে একটা interesting জিনিস হয়, as your spring returns, on average, I think though not true all the time, as your spring returns, it maintains the same elastic behavior. মানে back করার সময় the K is the same. Does it vary? Yes. But for our syllabus and other syllabuses, we assume on average লাইনটা similar ভাবে যায়। মানে লাইনটা এভাবে কোনো সময় যায় না, বা লাইনটা এভাবে কোনো সময় যায় না, লাইনটা মোটামুটি always কেমনে যায়? Parallel, okay? So what does this line represent, the one that I have drawn here? This line represents your material being loaded or unloaded. এই যে blue line-টা unloaded, right? It unloading. Or এই যে এই line-টা represents your material being loaded, right? উচ্চ process-টা এখন tell me something and pay proper attention as I explain this. The area that we have under this whole graph, right? Is this entire area here. Key represent for it, the entire area. Let me shade green the next thing. Yeah, so this entire area that you see here, right? What does it represent? Yes, very good. Pashidavas, right? So the yellow part that you see here represents the total energy you had provided toward the material, deform the material, right? But as you let it go, right? Here is so. Did you get back all of this yellow part? No. So get back part ponta, just the part that's under the blue line. Do you agree with me? So if you look at the part that's under the blue line, isn't that much smaller than what we initially provided the system? This orange, and this orange part that you see here is the energy you get back. And the yellow was what? The energy you had provided. Do you see there's a difference? Difference small part. That is very important in our syllabus. That represents the energy retained by the spring as it what? Broke the bonds. Do you understand? So whenever I take a spring and I provide 200 joules and I only get 10 joules back and 190 joules is missing, right? What was that 190 joules used for? For breaking the bonds, permanent deformation. Where does that energy eventually go? Breaking the bond can take a process. Breaking the bond is not a store. Store money energy to over. So once you break the bonds, what happens is the molecules split up and they fly. Fly money, they move out. And as they move out, they carry what with them? K, kinetic energy. And that causes the material to slightly what in the process? Heat up. And yes, now your material does heat up. So whenever you permanently deform a material, what does it get? Warm. Warm কেন হয়? Because bonds are broken and the energy is then transferred into the molecules and the molecules become more energetic. And that's where the material feels what? Warm. Okay? There are a lot of practical examples out there, but I don't think most of these you can relate. I'll try to explain, okay? একটা process আছে where you can hammer something, right? And if you keep hammering that thing, ওই objectটা আস্তে আস্তে গরম হয়ে যায়. Okay, so it is possible. But what does the material need to do in order for that to be possible? It needs to deform. So every time you hit something, right? Microscopic level, each molecule deform হয়. and the energy is taken by the molecule. So what does the molecule do in the process? Heat up. So if you keep hammering something, there's a video on YouTube, you can see that somebody tried to cook a steak by hammering it. যে সে হ্যাঁ স্টেকটাকে হচ্ছে হ্যামার করতে থাকবে একটা পয়েন্টে রান্না হয়ে যাবে, because that's theoretically possible, and the math was I think 150,000 times hammer করতে হবে, right? And he did that and it didn't work, and then the reason it didn't work was because every time he kept hammering, what he realized was the heat was also being lost to the surrounding, so it never actually heated up. Unfortunate, but yeah, it actually was tried. It is possible in theory. If you want to see this actually work, there's এটা বললাম এটা relatable না ওরকম. So do you know those aircraft carriers, ship থেকে যেখানে plane land করে ওইখানে there's this thing called an arrestor wire. So plane normally যখন land করে, fighter planes, right, they take like a kilometer to stop. You know, they have a lot of speed, but ওই aircraft carrier only has like 400 meters. ওখানে থামা যায় না. So ওরা কি করে, they put like a wire on the ship, right? আর প্লেন যখন ল্যান্ড করে প্লেনের নিচে একটা হুক থাকে, ওই হুকটা ওয়ারের সাথে আটকে পড়ে. And what does the hook and the wire do? Stop the plane. But the problem is the plane has so much K that wireটা প্রত্যেক ল্যান্ডিংয়ের সময় কি হয়ে যায়? Deform. And it deforms so much, right? You can see it turn red and melt because that's the energy in that. So ওরা সাথে সাথে এসে পানি দেয় উপরে, so you know, to cool it down. So that's like a very good example of where extreme deformation can even melt the metal, but you have to provide what? Very, very high energy for that. Okay, so yeah, that is the idea that's going on here. এখন হচ্ছে এই গ্রাফটাই হচ্ছে আমাদের বুঝতে হবে মেইনলি। আমি লেবেল করে দিচ্ছি পার্টস গুলো। Do you have any questions? এখানে থাকলে আমাকে বলতে পারো। ভ্যাকুয়ামে তো রেডিয়েশন যায়, radiation energy will still be lost to radiation. Yeah, the yellow region represents the energy dissipated. আমি এখানে নোটটা দিয়ে দিচ্ছি তাহলে ইজি হবে বুঝতে। I don't think you'll have time to copy this, but একটু দেখে নাও এদিকে সবাই স্ক্রিনে একটা জিনিস দেখাতে ভুলে গেছিলাম। Remember I told you that this line that you see here, এই যে দেখে নাও নিচে যে লাইনটা, the reverse line shows what? Your material going back. So if your material goes back and stops here, doesn't that show that there's a permanent extension out there? এই যে নিচের যে পার্টটা আবার দেখাই যারা দেখতে পারো না। So the materialটা এখানে এসে যদি থামে, that's its new length. তার মানে কি এক্সট্রা যে পার্টটা, isn't that the extra deformation? So that's something they ask you. So ওরা draw করে দিবে এই লাইনটা, তারপর they'll ask you what's the permanent deformation. You just need to check at this extra part there. Okay. Right, so next class here we will start stress strain Young modulus. Okay. You have a test on Sunday, dynamics and energy. Most of them.